have a chair in what's called carbon science at the University of Newcastle upon Tyne in England, and I've essentially been there for my full working career of Northumberland. And I, as a young person, left school and joined what was then the King's College, University of Durham, Newcastle upon Tyne, somewhere around about, I think it must have been 1941, right in the war period. And we completed our degree course and were through by just at the end of the war, 1945. Prior to that, the British Association for the Advancement of Science had meetings in Newcastle, and so had the Society of Chemical Industry. These meetings were much larger than they are now, and it was the practice to have excursions. Maybe 15, 20 buses would leave. And just by chance, by a rota system, I was asked to take a group down a coal mine in the west of County Durham in a place called Stanley. I'd never been down a coal mine before, though I was very familiar with the mining communities and with mining activities. So I took this group down the coal mine. Subsequently, I became the local expert on matters related to coal, and I took subsequent trips. And then, after graduating, we got a new professor in the department who was asked to really set up a new major initiative into coal research, and I was asked if I would join the group. Well, this was coming up now to about 1945, and I took that offer up, of course, and got a PhD in coal science in 1948. Again, by coincidence, one of the principal lecturers at that time left the university to join British Coal, which had been established and was running and had a new scientific division. For a person of that age, to have such an opening offered was quite incredible. So I was very much interested in research activities and travelling and aspects of teaching, and so I took up that appointment. Of course, I was very much a junior and worked under what was the great name at that time, Dr. H.L. Riley, who was subsequently replaced by a Professor W.F.K. Wynne-Jones, a Welshman of quite significant energy and character. And so we developed a career in carbon science, initially looking at coals of the northeast coalfields. There was some geological activity there whereby coals had been modified by dikes and sills in such a way that the coping behavior had been modified, and when these coals were placed into the traditional slot ovens, they generated quite considerable swelling pressures which tended to break at great expense these coke ovens, and so there was a need for research to look into ways of detecting these coals before they ever got into the coke ovens and could do their damage. That was really quite interesting because it got me down into the coal mines and to meet the local communities, and then I began to expand my interests, and we're now coming up, say, into the early 1960s, when I paid my first visits into the United States and into Europe. Of course, travel at that time was not by 747s, but by ship, by liner, cruise liner. And I remember my first crossing took 8 days. You do it in 6 hours now to get across the Atlantic. And that was really quite good, because it gave you a chance to relax, and you really had a holiday on board these boats at that time. Doesn't happen anymore, of course, unless you get yourself under the QE2 and have a small fortune in your pocket to pay for it all. I joined up at that time with the American Carbon Society and with the Gordon Conference organization, of course, which has always been of some interest, and which I've supported and actually on one occasion actually organized. Very strange for a UK person to do that, but I did get involved in that and put a good program together, which I still remember very, very well, of course. The laboratories at Newcastle then began to expand and get away just from the local coal story, and became interested in the blast furnace, coke, and even beyond that now, and moved into the area of surface chemistry, the area of active carbons, the generation of active carbons, the whole area of surface chemistry, adsorption theory. One of the things that I missed very much as a student was the fact that as a chemist I was trained to use a balance and weigh things rather than as a geologist who looks things in the microscope. Now, if I'd only been trained as a geologist, we did have access to a microscope. Polished sections of some of these coals that I'd studied, which had been modified by tectonic activity, such as dikes or sills of molten magma, these coals would have exhibited what we now call the generation of a liquid crystal phase. I missed that, and this was subsequently discovered by a geologist in the mid-60s, way down in the coal fields of North Ryde in New South Wales in Australia. That was a great revolution, actually, in the theory whereby pitch materials, pitch coals, coal tar pitches, general coals and materials, organic molecules, particularly polynuclear systems, were converted into the graphitizable or crystalline cokes, which form the basis of the aluminium industry for the making of their anodes, and also for the large, 1 meter diameter electrodes used by the steel industry in their crucibles for smelting purposes and the creation of special steels. Well, the story of liquid crystals and the way these liquid crystals can be controlled in size and shape became a dominant part of the laboratory for many, many years, and we attracted a great deal of attention from Japan, who wished at that time, of course, to further their own interests in the carbonization procedure, but wished to spin this mesophase into fibers, the so-called mesophase fiber. And so from about 1977 onwards, we had a very, very strong interaction with Japanese scientists. Of course, the story of the mesophase fiber, the liquid crystal fiber, still continues, and it hasn't really become a commercial success because the pan fiber, polyacrylonitrile fiber, the competitor, has always managed to keep itself well and truly ahead of the competition, and now, of course, dominates space applications in aircraft, and what have you. So I was in and out of Japan many, many times, interacting with people in Hokkaido and down in Kyushu and giving seminars, what have you, around the various industries. So that really was a very, very fruitful exercise.
You went to college in England during the Second World War?
Yes.
And what was that like? Was it disruptive, or?
It was, in one sense, living in the north, we were away from the, what you could call the Battle of Britain conditions, whereby the south really got blitzed. And I remember 2 or 3 occasions only when German raiders came over the coast. They attempted to bomb the bridges at Newcastle, because it was a bridgehead, without much success. And where I live at the moment, you can still see areas which were cleared out by German raiders who came in, simply hit the coastline, dropped whatever they were carrying, and disappeared as quickly as they could. Not all of them were martyrs in that particular game. The main impression, of course, was what you could call watching for incendiary bombs, night watching, where you had to take turns, allocations of being awake all night and monitoring the buildings, because there was a habit just to drop incendiary bombs. Now, if you could get at these within a few minutes, you could handle it just with buckets of sand, but otherwise you would have a very nasty fire on you, because they were really based on magnesium. And if you had buckets of sand, well, that quenched it. Otherwise, you could lose whole buildings. So that really was the most interruptive thing, because you weren't very good at lectures the next day when you'd really been up all night And that happened about, on a rota system of about once every 8 days, something like that. But otherwise, well, the other thing, of course, was that you had no vacations. It was considered that if you're running through the university at that time, then no time for vacations. So we would run the normal semester, followed by a 2-week break, and then another semester. So we really had a very intense course at that time. And I think that was probably it was the mechanical things which influenced you more than anything else.
And who did you work with primarily in your studies?
The leader was a man called H.L. Riley, who established the graphite structures, things like intercalation compounds. He opened up the structures of coals. He, in his own way, very significantly described the carbonization process of conversion of coals and pitches into carbons, but he couldn't hit the so-called liquid crystal story, whereby these pitch molecules, these large molecules, can form what we now call aromatic, pneumatic, discotic liquid crystal systems. These systems are now well established, of course, in the physics world and in display systems. And he only used the expressions, the carbonization principle. Again, as a chemist, he didn't use a microscope, and as a chemist, we tended to be rather too much in a hurry. So we used to heat things at 5, 10, 15 degrees per minute, and we really should have done it much more slowly and looked at the intermediate stages much more carefully. Of course, the geologists, and it was the geologists who discovered this, are more patient creatures, and very carefully took samples down the coal mine and, of course, examined polished sections of these, and lo and behold, by their high reflectance in the optical microscope, these liquid crystal structures came up. The work was done by a guy called Jeff Taylor, who was attached to the CSIRO at that time, and he was responsible for the publication. I remember on one occasion he came into the laboratories. He was visiting the geology department, but the head of that department had meetings that day, and he telephoned me up and said, "Marsh, I've got this visitor. I'm rather busy. Can you look after him for some hours?" So he came and he sat down at the table and re-encountered this discovery. He said it took 3 or 4 months before he ever dared begin to talk about it, because a geologist talking about liquid crystals in coal, he felt would have been quite silly. But after consultation with material scientists and others, he was finally persuaded to publish. Well, that revolutionized the whole world, because by realizing you had these liquid crystal systems, you could modify these liquid crystal systems, and so get different cokes of different types, of different properties and different applications. And it revolutionized the story of metallurgical coke. It revolutionized the story of the so-called delayed cokes, and introduced the possibility of making all types of artifacts synthetically once you knew how to make and control these systems. So that dominated the laboratories, again, as I said before, mid-70s, right up to the present moment. But like most subjects, we have got through the basic understanding process and moving now onto applications. So currently, of course, I think we, in the Northern Carbon Research Laboratories, which I am the director of now, and which has a staff of probably about, it varies, 20 to 25 people, including postdocs and students. This group is beginning to respond to the calls coming in from the environment. Now, perhaps in one sense, without being too sort of silly about it, we get the best of both worlds, because we have to study coal, which is a prime pollution generator, whether it be the nitrogen coming off as oxides of nitrogen, or the sulfur coming out as oxides of sulfur, or ash, which is coming away from the mineral matter of coal, or just general smoke. We have now to be able to understand and control and remove these emissions, because in the UK alone we burn something like, approximately 90 million tons of coal, and that's going to give an awful lot of carbon dioxide and other things. And on the other hand, you see, we're developing quite significantly now role in understanding the creation of carbons, active carbons, adsorbents, which will remove pollutions and clean up the situation, and to be able to predict the type of carbon we can get from a precursor and the way it activates to give really quite specific active carbons. In the past, it's been very much hit and miss, a black art. That's not to say, of course, that it was entirely hit and miss. Active carbon manufacturers these days know fairly well what they are doing. But there's a need to go beyond what we've been able to do at the moment to really fine-tune and get materials, active carbons, which very precisely can remove or separate mixtures of systems, etc., etc.
What have you seen as the biggest change during your career in coal science?
Well, initially, of course, if you were studying coal, you had approximate and ultimate analyses. You could say something about the fluidity of the coal or the hardness of the coal. You knew its swelling pressures, you knew its swelling capacity, and that was about it. At that time, when I was initially a student in the area, you had no idea whatsoever as to how to describe what is described now as the macromolecular structure of coal. It's not really correct to call it a polymer because there are no monomers, because each monomer, in quotes, is very much different from any other. And the advent of the modern NMR facilities, of FTIR, etc., have all been very, very responsible for further understanding the bonding, or the many types of bonding that exists within the coal material itself, and how this responds to solvent treatment and how this responds to thermal treatment. And that, of course, is very, very important these days, where you have to blend coals together to make suitable metallurgical cokes. The process of coal liquefaction, the process of coal gasification now, which probably will overtake coal liquefaction, which perhaps is going a bit out of fashion, being too complex. So over the years, you can see the basic application of modern analytical techniques to quite complex organic polymeric systems really is the biggest change.
How did you become involved with the journal Fuel?
I knew Dryden, who was an editor for many, many years, and during the very, very difficult period of the 1960s when coal research almost died, at the time of the very, very cheap petroleum sources, Dryden and I interacted very well indeed, mainly on the refereeing side, but in putting together and soliciting papers, because the quarterly, as it was at that time, was A5 and was running probably 100, 150 pages for a year. So this was no big deal. Now, of course, it runs at A4 and probably something like 1,600 pages. Now, Dryden, like all of us, of course, can't go on forever, and the stage was reached where he wished to retire as principal editor. But again, like many situations, a man who'd grown up with the situation can't be replaced by another single person. So the Butterworths, the organizers of Fuel, created an editorial board and created principal editors. And 2 or 3 of us were formed at that time to replace Dryden, who assumed the role of an honorary advisory editor during the transition period. During that time, of course, I acted as a general referee, but then began the policy of expanding the journal, of soliciting for papers around the world, of putting into a very aggressive marketing organization to promote Fuel. And then it came out of that very deep well where it almost went off the face of the earth, and probably would have done if it hadn't been for the personal dedication of Dryden to now a very prosperous and I would say, financially stable journal, one of the most stable journals that Fuel put out. And it has a readership of, oh, some thousands now of readership. And as I said, a page number of about 1,500, 1,600. So quite a successful journal now. That's been very interactive, and I enjoyed that very much. The Fuel staff, of course, are dominated by females, if I may use that expression, right down from the sub-editors to the principal managers within the organization. And of course, if you go and visit them, they're always excellent in selecting a very good restaurant, and generally taking care of you after you've had your business meetings. So very efficient. I like it very much, and I do learn quite a bit from them. They're organizing a meeting this September 1990 in Cambridge in the United Kingdom on coal structure. That, I think, is going to be a watermark, whereby we will be reviewing the aspects of coal structure over the past 10 years, and to have that as a permanent record, I think, which would be very nice, which hasn't been done really for quite some time.
How would you describe Dryden as a person?
Dryden as a person was very much a loner. He was a very, very intense and very efficient and very, very thorough researcher in the early days of what was called the British Coal Utilisation Research Association at Leatherhead in the United Kingdom. This was the principal coal laboratories. At the time when research associations were established after the war by the government, and the early or post-war papers, actually, of Dryden's are scattered throughout many, many issues of Fuel over that time. And I think he dominated very much coal thinking, not only in the United Kingdom, but worldwide. He was developing other methods for breaking into coal structure, principally on the use of solvolysis and the subsequent analysis, and the effect of rank, describing the changes in rank, describing the initial microscopic examinations, the reflectance, the massal composition. He was establishing at that time, slowly but surely, the very basis of what we call coal science as we understand it today. He enjoyed his editorship very much because as a one-man position, really, this suited him admirably. And he was meticulous in his editing, in his punctuation, the style of grammar, principally, shall we say, the way data were described, to make certain that there was consistency in units, so that any slackness or lack of clarity in the papers were removed. So not only was he a very good researcher in creating the data, he applied that same intensity of thought to the presentation of those data in the written page.
Now, did he interact with Stewart much at that time from the U.S.? Or?
I would have thought that he would have interacted significantly, probably by letter, because there was no fax, of course, and telephone communication was very primitive, and you didn't travel. You made a travel once a year. It was the big event of your life. I have no personal evidence for this, but knowing the man, he did keep in touch around the world. So I would have been most surprised if Storch and he had not interacted in some way, discussing or comparing information.
I probably will pronounce the name wrong, but Bonham of the...
Bangham.
Yes.
Bangham also, of course, was there. He is, I think, somewhat more of a flamboyant character, and he developed the so-called colloid theory of coal structure, which still pops up, but it all depends how you are looking at macromolecular networks and the point of view that you have of analysis. And I think probably overall the Bangham colloid theory of coal structure, as we now know it, is not quite acceptable. That may exist, of course, in the swamplands, the growth of the humic acid situations, but that's another story altogether.
You mentioned getting attracted into coal, but that wasn't even at that time considered, I guess, a hot topic. What special thing kept you going in that area?
I think what kept us going was the fact of the wide versatility of interests which you require to understand coal. First of all, you have to have some appreciation of organic chemistry. It is a porous solid. It is a porous solid with a very, very highly heterogeneous functional surface, much functionality in the surfaces, and so therefore it presents a challenge to the surface chemist. And in the same way as that those early days saw the development of a macromolecular approach, so it was the early days for surface chemistry. And you had the constant debates that nitrogen surface areas versus other surface areas, heat of wetting, and I got involved in this. And well, the other thing which we did at that time was to pull in the Russian literature. Probably heard of the DR equations or the Dubin and Radushkovich equations, which were used to describe coal structure and porosity in general. Now these arrived like a bolt out of the blue from the Russian literature, and they just worked. You made a log squared plot, and it just worked. But the rationale behind all this was not appreciated in the West, and it fell, I suppose, to our laboratories, really to my interest to try and understand what was happening here. And I remember being involved in many arguments and discussions in the United States and in Europe, whereby it said, well, you take any curve, any plot, and if you make a log squared plot of this, it's bound to be linear. All right, so I came back home, and my daughter at that time was aged about 9. I said, Rosalind, come on, draw out some curves here. And so she drew out curves which looked like isotherms, and apparently could have been isotherms. When you replotted this on the log amount adsorbed over the log squared, or whatever it is, P over P naught sequence, they weren't linear at all. Then we realized, of course, that the adsorption isotherm is unique to a porous material, and is describing, no doubt in a very heavily coded way, the structure within those materials. And curves which look like the shape of an isotherm, for some reason, are not describing that porosity. We were very lucky at that time that we had an engineer in the department who specialized very much in wave functions and related matters, and was very well acquainted with distribution equations. I remember discussing with him this DR equation. I said, look, can you give us an insight? Well, he said, looking at these equations, they look very much like the second derivatives of, say, Boltzmann's distributions or log normal distributions. He said, they'll be quite insensitive to that. And he said, it looks as though these equations are working for carbons because the adsorption potentials within the carbon must have statistical distributions which can be mathematically described and which are continuous. And so 3 or 4 days later, he produced a series of pages of mathematics of this. And that was the breakthrough. And from then on, we said that the Dubinian equation works because of the statistical distribution of adsorption sites. It's continuous of this particular format. And then it was taken up from there. Now, whether Dubinin, Radushkovich, the earlier workers were aware of this, we'll never really quite know. I've attempted to get into the Russian literature, but you can't pull it out. And a paper will describe a sequence, but it doesn't tell you why the paper was written and any of the early history. But I suspect that Radushkovich was a mathematician. I know he was a mathematician, and he may have had some insight which would indicate that this type of plot might work, and of course it did. Then, of course, you get on to the thermodynamic implications of all this, and so the subject develops. Until today, of course, not only are we handling regular systems, but we can handle rather unusual systems, in which the power term 2, comes replaced by 3 or 4 or anything between 1 and 2. Again, functions which are describing in quite a coded way something about the porosity in carbon materials or any other materials which are being looked at by this approach.
Did you ever meet Debenia?
Yes, I met him in Bad Soden 3 years ago at COP1, and I met him in 1982 at the Japanese Carbon Society meeting in Toyohashi. And you know, my hobby is of collecting photographs of people, and I have photographs of him in my album. And it was a very nice, very good occasion in Bad Soden in Germany in that would be 87. And I had a gang of students with me, and he obviously was very happy with this group of young people who obviously had, you know, heard of his name and could quote his name, but never actually seen him before. Very, very thrilled, a very, very humble man, who I understand still has vast quantities of information published significantly in the Russian language, you know, as we heard today, but really have to be got out. And I suspect that, you know, many, many good ideas or thought processes or material really is worth reading for, you know, because it's stimulating, may never ever get published because he's coming up to, what is he, 89, 90? I think he was born 1900 or 1901, something like this.
I understand he was a photographer. Did you talk to him about photography?
There were problems, of course, because his knowledge of the English language was very limited. And if you attempted to get off, you know, using such words as absorption and isotherm, he was very nervous and become very, very flustered. And as an old man, this frailty came through, so I cleared it away, and I never attempted to get into areas where he would feel this way. He always had an interpreter with him, and that did help enormously.
Well, who were some of the people that you've had good scientific debates with over the year?
Good scientific debates?
Yes, in the literature or on different subjects.
I suppose really in terms of the development of coal structure, looking at there, the people who influenced me most were really the Japanese. You had Yuzo Sanada up in Hokkaido, who was a very powerful stimulus, a man with a very dry sense of humor and very clear insight, who in a very interesting way, which is very difficult to describe, would stimulate me into thought processes. We had very strong interactions with Isao Mochida, who was at Kyushu University, who was an physical organic man who looked very much at the chemistry of the generation of these liquid crystal systems. And we interacted together very, very strongly indeed. The first postdoc I ever had was a girl by the name of Teresa Siemieniewska from the University, or the Polytechnic University of Wrocław, what used to be Breslau in West Poland. And the supervisor there was Yasienko, Stefan Yasienko. He was very much a carbonization man, and Teresa was very much a surface chemist. And this work that I told you about just earlier, about the development of the concept of continuous distributions of absorption potential, was done very much with Teresa Siemieniewska. And she was a very, very powerful supporting person indeed. Probably the person who had greatest influence on me was P.L. Walker, head of the fuel science group in Penn State, State College, Penn State, University Park, what have you. And every 2 years I would go over there and spend a summer sabbatical. And we covered many, many aspects of surface chemistry, of carbonization science, the development of liquid crystal. Sometimes just reviewing subjects, and you'll see some of these reviews published in Chemistry and Physics of Carbon. He's now retired, of course, which is a great shame. But we researched together and discussed together at length, very considerably. At Newcastle, I tended to be isolated because there was no one quite around me with the same interest. There was no other surface chemistry. There was no other solid state work. In fact, the chemistry as such was classical inorganic coordination chemistry, and the physical chemists around me were essentially working in the liquid phase. They were either spectroscopists or they were electrochemists. And so I missed the stimulus locally. There was a catalysis group which was of, shall I say, interest and use, because naturally it was a gas-solid phase reaction system, and so we could generally communicate. So I had to go out to the department dominantly to promote my interests and just have someone else to talk to at very considerable length.
What would you consider your most satisfying accomplishment in research?
What is very nice to hear was the fact that, say, here in COPS 2, young people were coming up and said, "Do you remember those 1965 papers?" "Yes." "I still read them, you know." "Yes." "A little bit old-fashioned," "Yes, but not much." "But really you got the message across." And in recent years I've attempted to simplify and pull out of the great debate of surface chemistry practical applications. You'll find that the surface chemist may study one particular carbon and he could take 4 or 5 months over it. But if you're working with a company that's manufacturing carbons, or you've got other problems and they're coming at you at a rate of 10 a day, then you have to adopt some form of screening. And so I attempted to pull out of the literature and describe such screening techniques which we could handle quite rapidly, which would ballpark your carbons, which you could then subsequently look at more closely at a later date. I enjoyed doing that very much. At the time I did receive some criticism from what I would call the more perfect surface chemists, who said this is very, very coarse work indeed. You really can't characterize a carbon like that. Well, of course you can't, but I wasn't interested in that. I was interested very much in placing them into categories, whether ultramicroporous, etc., whatever words you want to use. And again, at this COPS meeting, people have come up and said, "You know, we've used that paper of yours very, very considerably." And it's very nice when you are able to put your ideas and thoughts into press, and others, you know, are still using it. So I think around the world we have, and around the subject area in terms of adsorption chemistry, in terms of carbonization chemistry, which again we dominated the world with the liquid crystal story, have all proved very, very, very rewarding. And I find it very nice when young people or anyone comes along and says, "You know that paper you wrote?" "Yes." "We enjoyed that very much. We found it very, very useful to us." And that's what it's all about.
If you're going to describe yourself, how would you do that?
Very difficult question, of course, to look at yourself. I suppose really I'm what you could call head-driven. People do ask me this question. And I've always been this way, whereby if I see anything I don't understand, I just can't sleep. I can't relax. I can't do anything until I've dug into it and begin to get some rationale. And that's inevitable. It's almost like a very nervous situation, or almost like being on some sort of drug almost, whereby the drug in this case is problem solving. And so, you know, a university position, a research position, is an ideal way of handling this, except you never get it out of your system. You no sooner solve one particular problem and you have your debate and you write it up and you discuss it and it's finally published, and something else is coming along. And so always there are people knocking on your door wanting to discuss this, that and the other. And that's where my head works. The other thing is that I have enjoyed very much having young people around me. And of course the university researcher works in what I call a constant age bracket. He never ages, the students never age, because they're all in the same bracket, 20, 25, 26, and they were that 20 years ago. So it tends very much to keep you young thinking, because you're not getting the problems of older people, you're getting the problems of younger people constantly. And I find that very, very useful in terms of, you know, where we have to operate. And always a challenge. You never quite know what's coming through the door. No day is exactly the same as any other day. The phone rings, but the messages at the other side are always different. And this is very refreshing.
But when you try to get away from solving this problem, what hobby or what way do you do that?
For relaxation, generally, I think the things around the house. You know, I have small gardens, and I like gardening, which I find very, very useful. It's creative. I like to see things neat and tidy. I do like dogs, and in the early days when we were married, we had a dog. My wife had a dog, but then with the advent of the growth of the laboratories, much more traveling was involved. And you know, you can't take a dog with you. And my parents at that time could cope with the dog, so the dog got leased out, as it were, to my parents. Then they became too old to handle it, so we just didn't deal with dogs anymore. But I'd always stop for a friendly chat with a dog, you know, if the dog's quite prepared to have a friendly chat with me. And so we get on. I do enjoy meeting people, and as I travel, I do take a camera with me, and on this trip, for example, I'll probably take about 200 shots. And I put together a story, a sequence, and with the word processor, I'll write out some words, connecting words, and then I take them along to the local boundary to get all these things bound up. And I've probably got about 4 or 5 meters of these now. I do like to get over to the Lake District, or other areas in the United Kingdom, predominantly to walk. I do enjoy walking. My wife and I do this. And then that's about it, because I don't seem to have all that much time for getting away. I find it impossible, totally impossible, even in a place like Alicante here, to lie on the beach for 3 or 4 days. After half an hour, I'm fretful. I'm wanting to be up. I'm wanting to know what's going on around me. I just can't relax and let the world go by. And, well, so far I've survived all this, so I can't really see it being much of a problem. So I tend to have this incessant need to be active and doing something.
Yeah.
I would say 1990 is probably a turning point in the use of coal. Prior to this time, the thought could be that, you know, coal utilization processes just need to be tidied up a little bit to meet environmental issues. But talking to engineers, both within the United Kingdom and dominantly in the United States, it's apparent that new clean processes will have to be generated. You can't modify, you're going to have to rebuild and redesign. And so you have to see the role of coal in the new processes and how it will behave. For example, in very clean power generation, using the various types of, you know, topping cycle sequences or what have you. The behavior of coal mineral matter, mineral content is all going to influence efficiencies. And we will be looking at coal, nitrogen, sulfur emissions from coal, mineral matter, dust emissions, in terms of new systems altogether. So perhaps a lot of the data, vast amount of data which have been accumulated, will no longer have the relevance for today. So those of us who have to go out for research proposals, etc., will be putting out thoughts of coal in new processes, or not new applications, but new processings for established applications, mainly power generation, and alternative routings to chemicals from coal rather than liquefaction or the old distillation processes, which at one sense are obsolete now.
And how do these research proposals compare to the way research used to be funded when you were starting?
Each university research group now should have its own lawyer or attorney who could set about the writing, well, with advice of course, the writing of the proposals. They're becoming administratively very, very complex. The financing has become very, very complex, in which every penny almost has to be accounted for. And in terms of ratios of this monies to that monies, particularly if you're working across departments, makes life very, very tedious. In fact, a research director could spend all his time at the desk just handling the paperwork to get the contracts into what is essentially a modern legal format and seeing that it's being executed, by which time, of course, he's got no time left to undertake his research or do anything, or even see his students. That is the problem. At one time, I suppose, exaggerating this a little bit, you could get money coming in uncommitted, and at the end of 2 or 3 years, whatever it was, your reports went out, your theses were published, your papers were published. But people don't trust you anymore this way. They put some money on your desk and you have to account for every penny, how it's being spent, in quite a complicated way. And that's the major problem at the moment.
Do you see any way out of this?
It gets worse, because as universities, particularly in the United Kingdom, financially are under much stricter control with less money, apparently less money. Yes, it is in terms of real terms. So administration offloads some of its duties back onto the laboratories. So it's a growing problem. And at the moment, we're caught up in this, and I don't know how long it'll last, over the next 2, 3 years, or what have you. But the universities will have to break this problem, I'm sure, because if it doesn't, then researchers will just walk out of the system and say it's just not worth the effort. So much of your own personal energy is taken up to just make the organization work, long before you ever get round to the task of tackling the research projects.
If you were advising a young person on a research topic today, what would you?
Well, it's quite interesting actually, because at this COPS meeting there are young people who are sort of looking for work. They've got temporary work, but are really looking for something which is permanent. And because we're in the area of carbon, what I've been suggesting is that we are taking very seriously the developments of active carbons with specific applications. If you care to look at the literature or talk to anyone, if I said I wish a carbon should do these properties, can you make me one? There's no recipe, there's no logic behind it. We do not understand structure of carbon, we do not understand the activation process, and we really do not understand why particular carbons work in a particular way. And that, as I see it, is a task of the next, say, 15 to 20 years, whereby you're dealing with gas, vapor, liquid systems, water systems, or other systems. And this is the current need of society. And the way we're working now, that is where I would recommend. Now, these are people, of course, that I was talking to who had surface chemistry backgrounds, but not only do we have the general problems associated with the chemical industry, but you've got all the problems of water drainage, water runoff from soils, question of pesticides, insecticides, herbicides, whatever, as well as the cleanup of vast dumps of waste material, which are lying around, been around there for a century, accumulated the whole of the worst of the activities of chemical industry since, what, 1850, 1860, up to the present day.
If you were going to start over again, would you start in coal?
If I was to start all over again, I'd probably go into hotel management. That was something which attracted me at the time. Probably for very similar reasons, because running a hotel is a multidisciplined activity. Not only do you have to know how to run the kitchens, you have to know how to run the bar, you have to know how to run all of the domestic side of things. And I've always had an interest in running hotels. So if I were to start all over again, I really, provided everything else was the same, I might have gone into that particular area.
Do you have any other topics to add?
I suppose the things which really concern me at the moment, as an educationalist, of course, are methods of teaching chemistry as a growing subject. You see, it's expanded by a factor of, I don't know, 100, 200 since the early days. So you have probably factors of 2, 3, 4, 500 times more information than you had, say, 20 years ago. How to teach all this. And so I take interest in the methodology of teaching. I'm also very, very concerned of making students or young people articulate. In an average day, a student is listening probably 95% of the time and talking 5%. And I think that's very much an imbalance. And so when I get a chance in tutorial classes or other meetings of students, I say, I'm not going to talk, you do the talking. You come prepared and I listen, and we'll, at the end of the discussion, we'll discuss the discussion, see how you've got on. And that seems to work, because you put a student out into the big wide world, into industry. The first thing that happens is, the phone rings, the managing director is at the other end. Smith, come upstairs, I must talk to you. I'm off on the plane in 10 minutes. I want to know about this, that, the other. So you've got to marshal your thoughts and be able to talk very rapidly as you go up those stairs. And so to train a student in rapid thought and to be articulate in the same process, I think is very, very important. We've done that over the years, and all of the students, I think, have felt very, very grateful for having this facility, this expertise, this experience, I suppose, and this degree of personal security in the sense that they can do it.
Well, the science used to be viewed as something that matured slowly in the mind. Do you think the young have time to let that mature now, or have things changed so much?
A lot of pressure is put on young people. I think in terms of schools rather than universities, there's an element of speciality which is too deep. And the youngsters are coming up without a broad enough education. I think that is very, very sad in a way. But on the other hand, you see, the youngsters tend to be very mature. They've traveled a lot. They've got a much better experience. They're overall, I think, are much more articulate. And are capable of debating and discussing in a way which is better than, say, 20, 30 years ago, in the early days that I'm talking about now. So I'm, in recent years also, the students that have been coming through the university, particularly through chemistry, what I would call quite a nice bunch. I enjoy having them around. I sometimes take them home, we have a meal together. I don't mind having them around. They're a very nice group. And I think that's nice. We're getting mature, very sociably acceptable young people coming through. And it's amazing, actually, when you look at a 19 or 20-year-old. In one sense, they can be very insecure, they can be very immature, but on the other hand, they can be very, very creative. If only you can get them relaxed and feeling comfortable with you, then it's amazing the ideas which they can generate. Okay.